Welcome to this lecture in the ongoing series of lectures in linear algebra. Today we'll be proving something called the primary decomposition theorem. So let's start by recapping what we did the last time. So in the last two lectures what we proved is some property of the polynomials. The first one was Euclid's theorem, which says that suppose we have two polynomials over a field f such that the GCD of the two polynomials is dx, then one can find polynomials alpha x and beta x such that this kind of polynomial combination of ax and bx is same as the GCD. And using Euclid's theorem we showed the unique factorization property. We expressed it in a certain way last time, but this time we will say it in a different way. So what we have is we have a polynomial px which is non-constant. Then we say that there exists there is a unique scalar, and there are unique monic irreducibles such that they are pairwise distinct. Unique monic pairwise distinct irreducibles p1 up to pr. So by pairwise distinct we mean that pi is not equal to pj whenever I and j are distinct. That's what it means. So these are all distinct, and there exist unique positive integers k1 up to kr. This are the same, such that you can write px as take the scalar out and then this product of all the monics. So k1 is the number of times p1 appears in this product and so on. Exactly like in prime factorization, if you have an integer then you can write it as a product of 2 to the power k1 times 3 to the power k2, something like that. This is exactly the same theorem in primes. Alright, and before we continue, let us recall a definition, which was the definition of the direct sum, which was that suppose we have a vector space V and we have a bunch of subspaces, then we write V as, in this fashion. If every vector in V can be expressed as a sum of vectors, one in u1, the other in u2, and so on, and the last one in um, in a unique way. So for each vector v in capital V, there exist unique vectors u1 in capital U1 ... um in capital Um, such that V can be written in this fashion. And therefore, in particular, the vector 0 can be written in only one way, which is when each of these ui's are 0. So that's the definition of the direct sum. And now with this preamble, let us get into the material of this lecture. So first we'll prove a very nice lemma, which is as follows. So let T be a linear endomorphism on a vector space V over a field F, and let M1 up to MR be pairwise distinct monic irreducibles, or rather pairwise distinct relatively prime polynomials. We don't need irreducibles. Pairwise distinct relatively, or rather I should say pairwise distinct and pairwise relatively prime. So what does this mean? This means that when we pick any two of them, mi and mj, then the GCD of mi and mj is 1. So we have these polynomials, then the claim is the following. Then if we consider these vector spaces kernel of this particular endomorphism, and we take the sum. So we take the sum of these bunch of subspaces. The claim is that this is actually the direct sum of all of these. a very nice fact. So this is a subspace, so it is a vector space in its own right, and this vector space is basically a direct sum of all these subspaces is the lemma. So let's prove this. So we'll prove this by induction, which is basically a minimality argument. So clearly kernel of M1T, and I'll write it in a funny way. Well, so kernel of M1T is of course kernel of M1T. This is a tautology, which implies that, which is another tautology, and this looks completely funny. So I've done nothing so far, just completely mindless thing. So here is the thing. Suppose the theorem is false. Suppose the lemma is false. Then let J in this set be the smallest such that the following does not hold, meaning the following happens. This is a J. Maybe using a J is not such a good idea, but okay, it's notationally a little bit cumbersome, I and J, but what can you do? So let me explain what I'm trying to say. So if the lemma is false, then of course this does not hold. That's what falsity of the lemma means. So then there has to be some smallest integer in this range for which this inequality fails to hold, meaning if I replace r by that smallest integer, then this equality is not holding. Because if it holds for every integer in this range, then of course the lemma becomes true, and we are assuming that the lemma is false. We are going by way of contradiction. Okay, so there is a minimum such J, and what we have done by our tautology, this tautology of ours, which I am denoting by star. So by star, we know that J is at least 2. Alright. So therefore, by minimality of J, we have the following. Okay, so far so good. And now, since this is the case, there exists. Yeah, so before we go on, let us introduce a little bit of a notation. So let ui equals kernel of MIT. So just for convenience, therefore, this thing, which let us denote this by double star. Therefore, double star says that summation I equals 1 to j ui, this is not equal to the direct sum. And this implies, therefore, there exist u1 up to uj with u1 in capital U1 and dot 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 uj in capital Uj, such that not all are 0 and their sum is 0. So why is that? Basically, if this is not a direct sum of the ui's, then there is a vector here which you can write as a sum of vectors in ui's in two different ways. So if you just take the difference of those two different ways, you get this. So make sure that you get this point. It's a very simple point. So now we'll start doing something interesting. Okay, so what we want to do is, to get a contradiction, what we want to do is show that each of these ui's are 0. Because, that's how we will get a contradiction. We are assuming that this does not hold, which gives us a list of not all 0 vectors, such that their sum is 0, and somehow we will actually show that no, they have to all be 0. So let k be arbitrary, less than j, and of course greater than or equal to 1. So we fix such a k, and now by hypothesis, mi, mj and mk have GCD 1. Therefore, by Euclid's theorem, there exist polynomials alpha k and alpha j in fx, of course, such that alpha j mj plus alpha k mk, this is equal to 1. So which gives us that alpha jt mjt plus alpha kt mkt is the identity operator. Alright, and now we hit this by uk. So alpha jt mjt uk plus alpha kt mkt uk, this is uk. What we've done is we've just hit this hit uk by this operator and hit uk by this operator, so we get this. But note that this is 0, because uk is in the kernel of mk. Let me write that again. This is in the kernel of mkt. That's the definition of capital UK, and therefore this guy is 0. So what we end up with is that alpha jt mjt uk equals uk. Okay, so let's just box it. And now consider triple star. So from triple star, what we get is we hit triple star by mjt. And we get this, which implies mjt u1 plus dot 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 mjt uj minus 1 plus mjt uj. This is 0. But then again, by the same logic as the previous one, this guy is 0. So what we get is mjt u1 plus dot 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 mjt uj minus 1. This is 0. But here is the thing. Where does this guy lie? So the first guy is in u1 dot dot dot. The last guy is in uj minus 1. And the middle guy, the ith guy is in ui. So why is that? The thing is, each ui, let's see the definition of ui. Ui was defined as the kernel of mi. Where did I write it? Yeah, here it is. So ui was defined as the kernel of mi. So ui is t invariant. It just follows immediately that this is t invariant. And since it is t invariant, it is also pt invariant for any polynomial. Whenever p is a polynomial, ui is pt invariant. And therefore these guys, they lie in u1 up to uj minus 1. But by minimality, and this is a very important point, by minimality of j, we must have that this sum is equal to this sum, this direct sum. So since j is at least 2, this is a meaningful summation. If j were equal to 1, then this summation becomes meaningless. So since j is at least 2, then therefore this is a meaningful summation. And now, because of this direct sum, there is only one way to express 0 as a sum of vectors here, dot 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 sum of and a vector here. And this equation therefore will tell us that each of these guys are 0. So let me call this clubs. So clubs combined with the previous one, and so let's call this diamond. So by clubs and diamonds, we have mjtu1 is equal to ... mjtuj minus 1 equals 0. And this is hearts. Okay. So if we use hearts in the boxed thing, let's call this spades. So if we use hearts and spades, then we see that this thing is 0 because k is less than j. K was chosen to be less than j. This thing is 0, and therefore uk is 0. So by hearts and spades, we see that uk is 0. So what happened? We chose an arbitrary k less than j, and we showed that uk is 0. So now if we see this equation triple star, the first one is 0, the second one is 0, ... the penultimate one is 0. But that implies that this guy is also 0 because the sum of them is 0. So combining this with triple star, we deduce that all of these ui's are 0. This contradicts the earlier, this contradicts the choice of the ui's. We had chosen ui's to be not all 0 so that their sum becomes 0, and we could do this because our assumption that the theorem is false, which led us to this equation, and that's it. So not exactly a simple argument, but not extremely complicated either. So this proves the theorem. This contradiction means that the theorem cannot be false. Okay. Alright, so now we can state and prove the primary decomposition theorem. So again, let T be a linear endomorphism on a vector space V, and let assume that T is non-zero. I mean, that's, of course, there's nothing interesting to say about the zero endomorphism. So let mx be the minimal polynomial of T. So mx is already a monic polynomial, and let, by unique factorization, mx can be written in this fashion. Where m1x up to mrx are all pairwise distinct primes or irreducibles. Pairwise distinct irreducibles. Over F, of course. So far nothing has been said. It's just we took a non-zero endomorphism, we chose its minimal, we considered its minimal polynomial, and we just say that okay, factorize it. And now the statement is, then the vector space V can be written as the direct sum of these guys, mi t to the power k1 ki. So this is a endomorphism. This is the ki fold composition of that endomorphism. So a very nice theorem, and let's prove it. So yeah, before we prove it, let us recall a little bit from our past. So recall that if S and T are two endomorphisms, then we showed that the dimension of the kernel of the composite of S and T is at most the dimension of the kernel of S plus dimension of the kernel of T. So we showed that, I think we showed this in this lecture titled An Illustrative Example. That's where we showed this. And this is what we'll use, and basically what we'll use is just a little bit of a generalization of this. So if you have a bunch of endomorphisms, then the dimension of the kernel of their composites is at most this thing, the sum of the dimension of kernels of the individual endomorphisms. So we'll use this in the proof. All right. So what we have is that the entire vector space is the kernel of this guy, because mx is the minimal polynomial, therefore mt kills everything, and therefore we have this. Okay, and thus this is nothing but kernel of m1t to the power k1 dot mrt to the power kr. Okay, and now by our recollection, we see that the dimension of V is at most the dimension of the kernel of, let me write it as a sum in this notation, dimension kernel mit to the power ki. Alright, so we just used this fact here. Okay, but by the previous lemma, what we have is that this space which is the sum of the kernel of all these people is nothing but the direct sum. Alright, so what does that mean? This implies that the dimension of the sum of these spaces is equal to the sum of the dimensions. Right? But what is this? This is a subspace of V. So the dimension of this guy cannot be more than the dimension of V, which implies the dimension of V is greater than or equal to this quantity on the right hand side. Okay, so we have two inferences. The first one is, let me box that. And the second one, so for the first one we used this fact, and for the second one we used the previous lemma. What is the second one? The second one is this. Oops. Okay, so if we combine these two things, it basically says that these two dimensions are equal. So therefore, by the two boxes, we have dimension V is equal to the summation of the dimensions. So what that means ultimately is that this thing, the dimension of V is nothing but the dimension of the direct sum. Because this is precisely this guy. But this is a subspace. This guy is a subspace of the vector space V, and therefore this implies that V is actually the direct sum of these people, which finishes the proof. Okay, a short proof, but it uses the previous lemma, so well, in a sense not very short. And here is a little corollary. It's a result which we've already seen. So it says that let T be any endomorphism, then and let V1 up to VR be eigenvectors, be non-zero eigenvectors corresponding to eigenvalues lambda 1 up to lambda r, where I'm assuming that these lambda i's are pairwise distinct, where the lambda i's then the VI's are linearly independent. So we have seen this result before when we were discussing eigenvalues. And how does this theorem imply, how does the primary decomposition theorem imply this thing? So here is the fact. Basically, we already saw that the eigenvalues are precisely the roots of the minimal polynomial. So I'll just sketch this. So if mx is the minimal polynomial of t, then each x minus lambda I is a factor of mx. Why is that? Because lambda 1 up to lambda r are not the eigenvalues, but they are some eigenvalues. There may be more eigenvalues, but so these are definitely eigenvalues of t as given by the hypothesis. So since the roots of the minimal polynomial are precisely the eigenvalues, each of these guys are roots of mx, and hence each of these guys are factors of mx. So therefore mx can be written as x minus lambda 1 to the power k1 dot x minus lambda r to the power kr times qx, where qx is relatively prime. Qx does not have any lambda I as a root. So basically then it means that qx is relatively prime with this part. And if we apply primary decomposition theorem, then we get that v is nothing but kernel x minus lambda 1 to the power k1 direct sum dot kernel x minus lambda r to the power kr direct sum kernel qt. Yeah, so I should write, sorry, this is bad. I should write t minus lambda 1 t minus lambda ri. Yeah. So that's what the v boils down to by using the primary decomposition theorem. And now where does v1 lie? v1 is an eigenvector corresponding to lambda 1. So it is v1 is in kernel of t minus lambda 1 which is contained in kernel t minus lambda 1 to the power k1. So v1 is contained here, v2 is contained here, vr is contained here. And now this direct sum just immediately implies that these are linearly independent because these are non-zero. So I'll let you fill in the details. We used primary decomposition at this step. And yeah, so this illustrates the power of the theorem. We gave some roundabout proof of this. The proof of this was not exactly very straightforward. It was easy, but not completely trivial. And the primary decomposition gives this just as a simple corollary. It's a very useful theorem. Alright, so next time I will give some problems. I'll try to find some problems on minimal polynomials. Alright, so as usual, like, comment, share, subscribe. I also have Patreon. The link is in the description below. Thank you for listening, and I will see you next time.